Hello and welcome to the course Student Guide to Information Theory and Coding. In today's session, we will focus on the concept of prefix coding. In prefix coding, we have already discussed in more detail in the previous session that a code is called as a prefix code if it is defined as a code in which no code word is the prefix of any other code word. And these prefix codes are uniquely decodable code, and that's why they play a more important role in designing the variable length source coding technique. We also understood in our previous session the concept of the variable length coding technique. Now, in this session, our focus is to understand two typical prefix coding schemes. The first one is called as Shannon Fano coding, and the second one is called as Huffman coding. So today we'll discuss in detail how we can implement a variable length coding technique, a prefix coding technique named as Shannon Fano coding. So we are going to discuss the Shannon Fano encoding technique. Below are the steps for Shannon Fano encoding. Shannon Fano is a prefix code technique, and two steps for the implementation of Shannon Fano encoding technique are: arrange the symbols in decreasing order of probability. We know that a source contains certain number of symbols, and the occurrence of every symbol has certain probability of occurrence, and this probability of occurrence we know in prior. So if we know this particular probability of occurrence in prior, we have to arrange the symbols in decreasing order of probability. Step number 2, divide symbols into two groups such that sum of probabilities of each group are approximately same. It is not every time that we'll get the similar or equal division of two groups. That's why the word approximately same. Assign 0 to the first group members and 1 to the second group members, and we have to repeat step number 2 and 3 on each group until subgroups have only one member. So repeat step number 2 and 3 on each group until subgroups have only one member. It's difficult to understand looking into the steps written in the text matter, but we'll try to understand its implementation by taking a simple example for the implementation of Shannon Fano encoding. Let us write down the first example on Shannon Fano encoding. The information discrete memoryless source, just noted down the example. A discrete memoryless source has 8 number of symbols from M1 to M8. A discrete memoryless source has 8 number of symbols M1 to M8 with probabilities 16 by 32, 4 by 32, 4 by 32, 2 by 32, 2 by 32, 2 by 32, 1 by 32 and 1 by 32. You need to ensure that the probabilities which are given in this example, the total sum, it should be 32 by 32. Therefore, it is 16 plus 4, 20, 24, 26, 28, 30, 31 and 32. 32 by 32. Total probability of all the symbols will be always equal to 1. Now, implement Shannon Fano encoding algorithm. Implement Shannon Fano encoding algorithm and calculate the efficiency of the code. And calculate the efficiency of the code. I hope the example has been written. I will repeat once again. A discrete memoryless source contains 8 symbols from M1 to M8 with probability 16 by 32, 4 by 32, 4 by 32, 2 by 32, 2 by 32, 2 by 32, 1 by 32 and 1 by 32 respectively. Apply Shannon Fano encoding algorithm. Apply Shannon Fano encoding algorithm to and find out the efficiency of the code. Efficiency we have already defined earlier. Entropy, it is the ratio of entropy upon average code word length. So you need to find out the entropy, you need to find out the average code word length, and then you will get the efficiency of this code. But prior to that, let us try to see the implementation of Shannon Fano encoding as per the steps mentioned over here. So first step, arrange the symbols in decreasing order of probability. So arrange the symbols in decreasing order of the probability. If you look at here, the probabilities are already arranged in the decreasing order. So 16 by 32, 4 by 32, 4 by 32, and slowly they are going on decreasing. So all the probabilities, they are already arranged here in the decreasing order. In some of the example, if they are not in decreasing order, your first step that you have to follow is you have to arrange all these probabilities in the decreasing order. Now, what is step number 2? Step number 2, divide the symbols into two groups such that sum of probability of each group are approximately the same. Now I have to divide this particular thing into two groups, right? Upper group and lower group. So if I look at the first probability is 16 by 32. If I do the sum of all rest of the probabilities, 4 plus 4, 8, plus 4, 12, 14, 15 and 16. So I can understand that I can divide this particular group into two parts. First part is the upper part. First part, upper part contains the probability value 16 by 32. Lower part also contains the probability value 16 by 32. So I may say that it's an exactly equal division of this particular symbols. Upper part sum is 16 by 32, lower part sum is also 16 by 32. So I could able to divide them into two groups. Now, what is next step? The next step is assign zeros to the first group. Assign zeros to the first group and 1 to the second group. Now I'm going to do the same thing here. I have tried to divide it into two approximately equal parts. Now I'm assigning binary 0 to the upper part and binary 1 to all the values of the lower part. I hope the things are clear. Once again I will repeat. As per step number 2, I tried to divide the probability symbols into two approximately equal part. Upper part sum is 16 by 32, lower part sum is also 16 by 32. So I got upper part as M1 and lower part as M2 to M8. Step number 3, I have to assign 0 to the upper part and I have to assign 1 to the lower part. Now, what is step number 3? Step number 3 that I have already completed. Step number 4 says repeat step number 2 and 3 on each group, upper group and lower group until subgroup have only one member. So if I look at here, I try to divide them into two parts. I have assigned binary 0 to the upper part, but all lower parts I have assigned binary 1. Now look at here, upper part has only one element. So if there is only one element, I cannot do the division of the upper part, and here my process is going to end, right? My process is going to end at this particular point. So here I'm going to end this particular process. So I can just mention here E, right? End. Now I have to repeat this particular process for lower part. Now look at for the lower part. I will first take 4 by 32, first element. Rest of the sum is how much? 4 plus 2, 6 plus 2, 8, 10, 11 and 12. 4 by 32 and 12 by 32. They are not approximately same. So now I will take two bits together, two symbols together. 4 plus 4, 8 by 32. Remaining is 2 plus 2, 4, 6, 7 and 8. So definitely I can able to divide this particular group, the lower subgroup, at this particular interval, where upper part sum is 4 plus 4, that is 8 by 32. Lower part sum is 2 plus 2, 4, 6, 7 and 8. Exactly division with equal sum of the probabilities I could able to make it. Therefore, I will now repeat step number 3, where upper part I will assign 0, 0, lower part I will assign 1, 1, 1, 1. Okay. Now, once again I look at the upper part. In upper part there are two elements, 4 by 32, 4 by 32. So one more division I could have here at this particular juncture. I could able to divide this thing as 4 by 32, 4 by 32. Upper part I will assign 0, lower part I will assign 1. There is a single element, so I have to stop the operation. There is a single element, I have to stop the operation. Now I will focus on lower part. 2 plus 2, 4. 2 plus 1 plus 1 is 4. So my next division is going to be in the lower part, where I could able to divide 2 elements in the upper part and 3 elements in the lower part. I will assign 0, 0 to the upper part, 1, 1, 1 to the lower part. Once again in the upper part there are 2 elements, so I could able to divide them into 2 parts. So this division will have occurred here, and I will assign binary 0 to the upper part, binary 1 to the lower part. Here my procedure will stop because it contains single element. Similar thing I can do now for the lower part. Here it is 2 by 32. Here it is 1 by 32 plus 1 by 32, 2 by 32. So the division will be carried out here. Upper part I will assign binary 0. Lower part I will assign binary 1. Here there is a single element, so my process will get stopped. Again, for lower part there are two elements, 1 by 32, 1 by 32. Upper part I will assign binary 0, lower part I will assign binary 1. Here again the single elements, I need to stop my process. So this is what the implementation of the Shannon Fano encoding technique with the steps that we have discussed. I hope the things are clear to you. Once again, I will repeat the steps. Step number 1, arrange all the probabilities in the descending order. Step number 2, divide the symbols into two groups with approximate sum equal for the upper part and for the lower part. This is an ideal example where for every case, my upper part and lower part sum is exactly equal. But in some of the examples, this upper and lower part may not be exactly equal. In that case, you have to take the benefit of approximate equal sum. So that approximate equal sum will try to give the closest difference between the sum of the upper part and the sum of the lower part. Step number 3, upper part you assign binary 0, lower part you assign binary 1, and continue this particular step until you have single element in the upper or lower part. That way you could able to generate the code words for the symbols M1 to M8. So if I look at the solution, the final code that I got for first symbol M1 is 0. For symbol M2 it is 100. For symbol M3 it is 101. For M4 1100 and so on till M8 5 times 1. Now if I look at the concept of prefix code, the concept of variable length coding, I observe that the probability M1 is highest probability in this particular source, and highest probability means it carries less information, and as it carries less information we have encoded this with a single bit only. As the probability go on decreasing, the amount of information that we are getting from this symbol will go on increasing, and therefore the more informative symbols, they have been encoded with more number of bits. So as the probability is going on decreasing, the number of bits per symbol, it will go on increasing. Lowest probability, highest information, and it should be represented by large number of bits per symbol. I hope the things are clear to you. Now, what is the next task in this example? You have to calculate entropy for this particular probability symbols. Entropy, we already know the formula for the entropy. H of S. H of S is nothing but summation k is equal to 1 to L pk log of 1 upon pk to the base 2. If you calculate the probability of all these symbols, the entropy will come down to 2.3125 bits per message. Then you have to calculate the average code word length. Average code word length formula we have already know, summation nk into pk. Nk is the code word length, pk is the probability. So we have already used this particular formula in the earlier example where I tried to show you the formula for r bar or L bar, that is summation k is equal to 1 to 4 nkpk, and the formula for the entropy summation k is equal to 1 to n pk log of 1 upon pk to the base 2 or minus summation pk log of pk to the base 2. So by using these two formulas we can calculate the entropy h of x and average code word length, and from that the efficiency, which is h upon L bar, h upon n bar, or h upon r bar. So these are the variety of notations we observed for average code word length. The notation L bar, R bar, and N bar, all these three symbols used by different books, they represent average code word length, and the efficiency of this code H upon L bar is 100%. That's why I mentioned that this is the ideal code where you could get the division of exactly equal probability groups, and that's why the efficiency of this code is 100%. But for all practical purposes, there are many codes whose efficiency is close to 100%, and they are not being divisible exactly in the upper group and lower group. That's why in the step we mention the concepts of approximately the same. Each group are having sum of probabilities approximately the same. So this is what the example of Shannon Fano encoding technique. I hope I could able to explain you the algorithm in the simplest way by taking a simple ideal example where the efficiency is exactly 100%. If you have any doubt, you can please ask so that I can. Okay, so now we'll do try to look at to the second example of Shannon Fano encoding. Write down the example. Apply Shannon Fano algorithm. Apply Shannon Fano algorithm for a source which generates 7 symbols with probability 0.2, 0.4, 0.04, 0.08, 0.08, 0.12, and 0.08 respectively. Apply Shannon Fano algorithm for a source which generates 7 symbols with probability 0.2, 0.4, 0.04, 0.08, 0.08, 0.12, 0.08 respectively, and calculate the efficiency of the code. So look at the solution. We need to apply the Shannon Fano coding algorithm for a source which generates 7 symbols with probabilities given respectively So as per the step number 1 of Shannon Fano coding algorithm, we have to arrange all these probabilities in the descending order. So M1 is 0.4, then 0.2, 0.12, 0.08, 0.08, 0.08 and 0.04. All these particular probabilities are arranged in the descending orders. That is step number 1 for Shannon Fano encoding. Step number 2, divide these particular symbols into two groups containing approximately equal probability. So first I'll take the first part, that is the first probability, and in the first probability first group I got zero point 0.4 value, and rest of the sum if I did it, it is coming down to somewhere zero point 0.6. This is what the first option that I created with 0.4 and 0.6. Therefore, if I just want to divide it into two equal parts, I could come down to know that the division is carried out. First group contains 0.4 value and second group contains 0.6 value. These are two approximately equal values with which I could able to divide this group. Upper part, step number 3, I will assign binary 0. Lower part, I will assign binary 1. Upper part, there is a single element, so I need to stop this process, and now I need to focus on lower part. Now for lower part, if I take the first element together, that is 0.2, and rest of the elements sum, it is 0.4. The difference between 0.2 and zero point 0.4 is quite large. Therefore, in grouping, now I will take two bits together. So I will take zero point 0.2 and zero point 0.12 together. This sum is 0.32 and this sum is 0.28, 26. So the difference is 0.04. Therefore, the division I could able to do upper group 2 elements, lower group 4 elements. Again, as per step number 3, upper group I have to assign binary 0, lower group I have to assign binary 1. So binary 0, binary 1. Upper part, there are only two elements, so I will straightway divide them into two groups. Upper part I will assign binary 0, lower part I will assign binary 1. There is a single element in both the parts, the procedure stops here itself. Now I need to focus on lower part. In lower part, if I want to divide them into two equal group, I could get the division here as 0.08 and zero point zero 0.08 is 0.16 and 0.08 and zero point zero 0.04 is 0.12. So the division I could able to do here into two equal parts is I can able to divide this over here. So I got 0.16 upper part, 0.12 lower part. Binary 0 is assigned to the upper part, binary 1 assigned to the lower part. Upper part consists of two groups, so it will get straightway divided into two parts. Upper part binary 0, lower part binary 1. Similarly, the lower group is also have only two elements divided into two parts, point 0 upper and point 1 lower. Both contain single elements. The process gets stopped here itself. So this is the way how we have repeatedly divided the entire group into into two subgroups with approximately equal probability values. Then I will get the final code, that is the code for zero point 0.4 is 0, for M2 it is 100, M3 it is 101 and so on till M7 it got 4 times 1. Once again here we would like to prove the concept of the information theory, where highest probability value it contains less information, therefore encoded into less number of bits. As the probability is going on decreasing, we observe that the length of the code is going on increasing, because lesser the probability, more is the information, and if more information, the symbols are coded with more number of bits. So this is how we can implement Shannon Fano encoding technique. For this technique, then we can calculate the value of entropy by using the formula summation pk log of 1 upon pk to the base 2. The entropy bits per symbol or bits per message is coming down to 2.42 for this particular code, and the average code word length R bar or L bar, which is summation k is equal to 1 to L n of xk plus p of xk, and n of xk is the length of the code word. The length of the code word here is 1, here it is 3, here it is 3, 4, 4, 4 and 4. So we observe that by doing the multiplication of n of xk with p of xk and summing over the L values, we could get the average code word length as 2.48 minutes per message, and from that the efficiency of the code eta will be h upon L bar, which is 97.6% for this particular code. So this is what the second example that we have understood for Shannon Fano encoding algorithm. Okay, so in previous section we have understood the Shannon Fano encoding algorithm, which is the variable length coding algorithm, which follows the conditions of prefix coding. Now there is one more algorithm which we can use for the variable length coding implementation of source encoding technique, that is called as Huffman encoding algorithm. Let us try to understand how we can implement this Huffman encoding algorithm. What is the algorithm? First we'll try to understand the steps of the algorithm, and then we will see its implementation by going through one typical example for Huffman encoding algorithm. So let us first try to understand what are the steps for the implementation of Huffman encoding algorithm. Step number one is very similar to the step number one